So we're going to continue with list oblivious transfer and applications to run optimal black box multi-party coin tossing from Michel Ciampi, Raffaele Ostrowski, Luisa Sinistrozzi, and Henrik Waldner. And Henrik is going to give the talk.
Yeah, thanks for the introduction. So I'm also going to start with another introduction to MPC. So in MPC, we have multiple parties with different inputs. Now better? Okay. So yeah, we have multiple parties who each have their individual inputs, and their goal is to compute a joint function over their inputs. And what they're going to do this is they're going to interact in multiple rounds of communication. And then in the end, each of the parties receive the final output of the function. And of course, what we want here is we want to have some privacy guarantees. Otherwise, this whole thing would be trivial. Each party could just output their input and everyone could compute the function. But of course, we want to guarantee that malicious parties cannot learn the input of honest parties. And yeah, we capture this using a simulation-based security where we have a real world where the adversary is interacting with the real parties. And we also have an ideal world where the adversary is interacted with simulated messages. So he's only receiving simulated messages that are generated using the final function output. So yeah, intuitive, we have security here because in the simulated world, the only information that is used is the information of the final function evaluation. Right, and in this setting, we are also considering malicious security, so the adversary can behave as it wants. We're in the plain model, so we don't have a CRS or random oracle. And yeah, the simulator makes black box access to has black box access to the adversary. And yeah, it's also dishonest majority setting, so the adversary can corrupt all but one parties. And yeah, we are focusing on constructing round optimal black box MPC. What do we mean by this? By round optimal, we mean that yeah, we want the parties to only interact in 4 rounds, which has been shown to be the necessary requirement. And in a few other works, this lower bound has also been matched, so this is also sufficient. And black box here refers to the use of the primitives. So the primitives are only used in a black box way, meaning that only the input-output behavior of the primitives is used. And yeah, we cannot do anything like zero knowledge proofs or something like this that would access the code, the description of the primitives. And yeah, like this might have some practical advantages. And yeah, the current state with this is like also with respect to the previous talk, there is this 5-round protocol from 2021. And there's also the 4-round protocol that we have just seen from sub-exponential secure assumption. And in this work, we are presenting a 4-round black box secure MPC protocol for inputless functionalities from standard polynomial time assumptions. And this protocol also works for general functionalities against some special type of non-aborting adversaries. Yeah, before we see how our protocol works, we're going to recap this IKSS work from 2021. So the primitives that they use, so they rely on this IPS compiler, and they use 3 different types of primitives. They first use a semi-malicious 4-round MPC protocol, where an adversary can essentially determine the randomness that is used to generate the messages. There's also this N-client M-server protocol that works in 2 rounds, and a 4-round non-mailable K out of NOT protocol. Right, so in this client server setting, we have N different clients, each holding their own input. And now they're not interacting with each other, but they're going to send their messages to some trusted servers. And then those servers are going to do the computation. And afterwards, each of the server outputs the messages to the different parties, and the parties are able to compute the final function evaluation with respect to the inputs of the parties. And yeah, this protocol is secure against an adaptive malicious adversary as long as it only corrupts n-1 divided by 3 of the servers. Right, this is the first primitive for this previous work. And the second one that we need is the K out of NOT, where we have a receiver that has as an input a set of indices of size K, and a sender who has N different inputs. And then they're going to interact in like 4 rounds of communications. And at the end, the receiver is going to learn the desired input from the senders. Right, and in this previous work, they're actually going to execute this protocol in parallel multiple times. and this is where some non-malleability is required, and this is what they call a watch list. And they realized this by using a two-party computation protocol as well as some split-state non-malleable codes. So how does the protocol actually work? So we're only focusing on the two-party case here, but for the other parties, it follows in an analog way. So in the first step, like, we are executing multiple of these semi-malicious protocol, and each of these protocols is going to simulate one of these servers in this client-server protocol. So yeah, the parties are using the input with respect to this client-server protocol. And in the end, they can simply, they obtain the output over all these M instances of this MPC protocol and can compute the final function evaluation. The problem with this protocol right now is that it has the same security as the MPC protocol, so we don't have malicious security yet. And to obtain malicious security, we're going to do a cut and choose using the OT to check that every party has behaved correctly in a certain number of instances in the simulation. Right, and then before the parties actually output the last round of this computation, right, which would reveal some information if the other parties would behave maliciously, they're going to verify that the cut and choose is correct. Right, and as already mentioned, this is now a 5-round protocol, but we would like to do something in 4 rounds. And we can clearly see that the bottleneck here is this OT protocol, which takes 4 rounds. So the question is, can we do it in 3 rounds? And yeah, this question has already been answered in the previous talk. Well, we can't because of an impossibility result from Katz and Ostrovsky. So what we're going to do to circumvent this possibility is we're going to consider a weaker notion of security that we can realize in 3 rounds and show that it is sufficient for the application that we want to have. And this notion is what we call list OT, and this is based on the list coin tossing notion from this work on promise zero knowledge. And this intuitively means that the adversary has some choice over the output that is being obtained. So yeah, we have the receiver and the sender here in the ideal world, and they have access to this list OT functionality. And what the receiver can now do is it can submit its input bit B for the OT, as well as the value kappa. And then what the list OT functionality is going to do, it's going to sample kappa OT instances, essentially, right? So here, this is a random OT, so it's simply going to sample 2 times n random values, 2 kappa values of size n. And then it's going to forward all the values with respect to the choice bit of the receiver to the receiver. And now the receiver has this kappa different values and can choose freely which one of those values it would like to accept. Right? They're all random OT values because they've been correctly generated, but yeah, the receiver has some choice which of these ones it wants to be used. And then in the last step, the corresponding value pair is output to the sender. We also consider a generalization of this notion for 2-party computation, which we need later in the final construction of the protocol. And the ideal functionality here is designed in a very similar way. So, but this time the receiver doesn't only have a bit as an input, but a value y from the input space of the function. Then the ideal functionality is going to sample an input on behalf of the sender corresponding to some distribution, and is going to do the evaluation of the function over all of these values for the sender as well as the input given by the receiver. Then in the next step, the output of the function is again sent to the receiver. The receiver can choose which one of those it wants to accept, and then the sender learns the corresponding input that it has in this computation. Right. Yeah, having introduced this notion, coming back to the more restrictive setting, because we only need the 2-party computation in the final construction. So the next question that we would ask is like, how can we realize such a protocol in 3 rounds? Like, what would the simulation strategy be? And yeah, so the idea is now that we would have the simulator that is interacting with this malicious receiver, and it has to provide the values for the list OT functionality, which is the input bit, as well as the value kappa to know how many values to sample. So what the simulator is going to do, it's going to receive the first message from the receiver, which will be generated with respect to its input bit. And then it's trying to use some rewinds with respect to the second and third round to extract the input bit from the receiver. So this can be like, again, like some cut and choose, asking the receiver some challenges, and then, yeah, being able to extract the input bit B. And during the simulation, to simulate like these second round messages, the simulator would sample the inputs according to this OTL functionality by itself. And once it has extracted these inputs, it would forward them to the OT functionality, would receive as a reply the correct values, as we've seen in the definition before. And then again, would try using multiple rewinds to force one of these values onto the adversary. So it would use the first value that has been output, generate a second message with respect to this. If the adversary doesn't provide an accepting third round, it would try again with the next message, and so on and so forth, until the receiver accepts. And then it can forward the corresponding index to the ideal functionality. Right, so yeah, we would use the rewinds here for the extraction of the input and for forcing the output, and then telling the ideal functionality which value has been used. Good, now that we know the simulation strategy, we can think about how to construct a protocol like this. And what we're going to start from is a sender private OT protocol. So we don't have the simulation security for this protocol. We consider a weaker notion. And this is a notion that we can realize in 2 rounds, where what is essentially guaranteed is that if the sender has like either using as an input S0 and S1, or in both of the positions, the value that the receiver obtains, depending on its choice bit, that this is indistinguishable for a malicious receiver. This is this notion that is known as statistically sender private OT. And yeah, as already said, and as we can also see, this protocol has only 2 rounds. So the hope would now be to modify or to add some things on top, such that we can get our notion in 3 rounds. And the first idea that we could try is to do a combiner and then ask to open some of the positions, right? So we would still protect the privacy of the receiver in the honest protocol execution. But in the simulation, we would hope to use that trick to extract a bit of the receiver. So how could such a combiner look like? Well, in the first step, what the receiver is going to do is it's going to secret share its input bit. And then it's going to execute essentially 2 OTs, where it in one OT uses one of the shares as an input, in the other OT it uses the other share as an input. And then the sender would generate also some secret shares that kind of work with the secret sharing scheme of the receiver, meaning that if the receiver receives the corresponding shares with respect to B0 and B1, it is able to reconstruct the value as B0 XOR B1. So yeah, the sender is simply going to execute the OT using these special generated shares. And yeah, for the check of correctness of the executions, it's also going to sample a challenge bit that it also forwards to the receiver. Yeah, then in the next round, the receiver can reconstruct its input, like the value that it was asking the sender for, and it can also provide the opening for the corresponding challenge to the sender. Good. Right, this is a first approach to construct this list simulatable OT protocol. The issue here is, though, that it's still not possible to extract, because we can imagine a malicious receiver that would never agree to open the second OT. So we would kind of be stuck by only learning one share in the simulation, and therefore we cannot finish. Right, so one idea to fix this could be to just repeat this protocol multiple times. So this is how this protocol would look like then. The receiver would essentially share its input bit 2 times and then run 2 executions in parallel, right? This is exactly the same protocol as before. And then in the end, yeah, the receiver would reply to both of the challenges sent by the adversary. And now the hope would be that, like, yeah, if we can open both of the positions in one of the many repetitions, that we are able to extract the input. Unfortunately, another issue arises here, and this is the issue that the adversary can use different inputs across the different instances. So to fix this, we kind of need to make sure that the receiver is only able to reconstruct its input if it has behaved correctly in all of the repeated executions. And we're essentially going to do this by modifying the secret sharing that both of the parties do with respect to their inputs. So yeah. So we're going to start again with the receiver having input bit B, and again computing a standard n out of n secret sharing scheme. And then it's going to also generate this value di, which is equal to the bi share XOR with its actual choice bit. Of course, this doesn't make so much sense in the 2-input case, but yeah, we can imagine that we have an n out of n secret sharing scheme here. And then the receiver is going to start like multiple OT executions with respect to each of these values. So using B0, D0, B1, and D1. In the next step, what the sender is going to do, it's also going to compute an n out of n secret sharing for its inputs, and it's going to sample some encryption keys for all of these shares. And then in the next step, it's going to generate the 2 pairs of ciphertexts in such a way that the receiver is only able to reconstruct to obtain all the shares with respect to one value if it behaved correctly. So the idea here is to create in this CT0 pair to use the key 0 key to encrypt the S0 share and the key 1 key to encrypt the S1 share. And in the CT1 pair of ciphertext, we kind of switch the roles of the keys. And now, with respect to the way in which the values di and bi are sampled, we're going to reply in the OTs in such a way that you only obtain the correct care and ciphertext pair combination, such that you are able to decrypt the share that you were asking for. And this follows from the relation of di and bi. Right, so this is then what the receiver would do in the final reconstruction. And yeah, then in the last step, it would answer to all the challenges that are given by the sender. And yeah, now everything works as we want it to work. Right. Yeah, this is just one of the building blocks that we need to obtain our final results. So let me tell you what other building blocks we need or how we like continue from here. So we have this protocol now, and we're going to amplify it and add some type of rewinding security. And we also use this to construct a K out of N list OT protocol, which we then use to realize a list 2PC protocol. This list 2PC protocol is then used to create this non-malleable list K out of NOT, right? Which we can then run in parallel multiple times to get this 3-round list simulatable watch list. And then this can be used to construct a 4-round MPC protocol in the same flavor for this IPS compiler that we have seen in the beginning. And yeah, for these last 2 transformations, we orientate again on this work of Ishai et al. From 2021, but we of course need to make some modifications and add some more steps to make everything work with respect to this list notion. Yeah, thank you very much.
Thank you so much. There's a lot of time for questions. If you can come in front of the mic. Oh, I thought that was a question.
Yeah, that's fine.
Can you talk a little bit about the modifications, and also I want to know exactly what are the exact computational assumptions?
So we can do this from polynomial. So we only need the statistical sender private OT essentially, right?
Oh.
Which we can do from polynomial DDH, DCR, whatever we want, right? And yes, so yeah, to realize this, sorry, what was the first question?
About the modifications.
Right. Yes. So this inner protocol, we need to use a simple, this similar inner protocol to what we've seen in the last talk. So we also need to reduce it to 4 rounds, to 3 rounds, because when we run the OT in the beginning, right, we need to extract from it. So we can't do the first round of the OT and the first one of the MPC in parallel. And yeah, then we also need to make sure that those protocols kind of work when we sample the values from this distribution that we have in the ideal functionality.
I see.
Yeah.
Okay, then let's thank the speaker again. Thank you so much.
Okay.
Can you try the clicker?
Sorry, the clicker. Mhm. No.
Okay. So next we have security preserving distributed samplers.
Huh?
How to generate any CRS in one round without random oracles. From Damiano Abram, Brent Waters, and Mark Zandri. And Damiano is going to give the talk.
So, hi everybody, and thank you for the introduction. And yeah, I have to say that I'm happy that this is the last session because if I go over time, nobody will get too angry. So, in this today, I'm going to talk about a follow-up project of our Eurocrypt 2022 paper about distributed samplers. So, let's get started. So, if there is something that I guess kind of bothers me in cryptography is actually trusted setups, because I feel they don't get the attention that they actually deserve, in the sense that many times we take them as something that comes for free, when actually they come with all kind of issues. In particular, for instance, many times we cannot implement them using a random oracle because they have structured outputs. Then there is the issue of actually agreeing on who the trusted third party is. Then also, if we consider the cost of this trusted third party, sometimes they are high. For instance, if we want to generate correlated randomness, the communication is usually high. And also, the trusted third party always needs to be online, ready to answer any request that the parties have. And finally, there is the most important problem, namely that trusted third parties are inherently a single point of failure. So if an adversary takes control over them, then the security of the protocols that rely on these trusted third parties is completely broken. Okay, so in order to solve all of these issues, in Eurocrypt 2022, together with Peter Scholl and Sofia Yakubov, we introduced this cryptographic primitive called distributed sampler. And basically, this is a one-run protocol that implements the functionality used in the slide. Basically, it generates a sample from a distribution D, and it provides it to all the parties without leaking any additional information. So formally, what happens in this protocol is that everybody speaks at once, and after this only round of interaction, everybody is able to derive the output by just running a deterministic algorithm on the transcript. And so you can notice that even an external observer can compute R, because all it needs to know is the transcript. Okay, this immediately gives a secure protocol that generates a CRS for any MPC protocol using only one round. But actually, we can obtain something more, because in the Eurocrypt 2022 paper, we show that if distributed samplers exist for any efficient distribution, then we can generate large amounts of correlated randomness using only one round and with sublinear communication, in particular logarithmic. Okay, this sounds great, but are we actually able to build distributed samplers? And yeah, we started answering this question in the Eurocrypt 2022 paper. We started from the semi-honest model, and we built distributed samplers for any efficient distribution in the plain model, so no random oracles or CRSs. And yeah, based on rather strong assumptions, in particular I/O and multi-key FHC. And yeah, it turns out that I/O is actually needed, because distributed samplers for any distribution plus LWE imply I/O. Okay, anyway, here we are in the semi-honest model, so not the strongest security guarantees. What about active security? And here we started having some problems, because the functionality here in the slide cannot be implemented against active adversary. And this is an immediate consequence of Cleave's impossibility for coin tossing. And yeah, basically the issue is that we have to allow the adversary some influence on the output of the protocol. In general, there is a whole class of attacks that we cannot prevent, and it's an issue that is common to all one-round MPC protocols. Essentially, here the adversary is active, so it can use rushing. It will wait for the messages of the honest parties, and it will start rerunning the protocol in its head many times, fixing the messages of the honest parties as in the real protocol, and regenerating the messages of the corrupted parties each time. In this way, it obtains many different outputs then it can choose the one that it likes the most, and it will send the messages of the corrupted parties for that execution. And the output will be exactly what it chose. So this is something we cannot prevent. So in the Eurocrypt 2022 paper, we defined the functionality for active security as follows. So it is split into two parts. First, the adversary interacts with the functionality. It queries for as many samples as it wants. And yeah, when it finds something that it likes, it will just tell the functionality, output this to all the parties, and the functionality will just follow the instructions. And yeah, what I like to argue is that if this functionality is used to generate a CRS for an MPC protocol, this CRS is still secure for the application. And that's because, yes, the adversary can choose the CRS it wants, but in a set of polynomial size. So with overwhelming probability, or these CRSs will be secure. Anyway, with this definition of security, we build actively secure distributed samplers for an efficient distribution in the programmable random oracle model, and essentially on under the same assumptions, IO, multi-K FHC, and NISX. And yeah, the issue was that it was the programmable random oracle model, because random oracle don't exist, and programmable random oracles are even worse. So the natural question was, can we get rid of random oracles completely? And yeah, in a subsequent work, we answered this question, and the answer is no. It's a subsequent work that is not the paper I'm talking about today, actually. So formally, we proved the following theorem that says that actively secure distributed samplers always need a CRS. But this CRS is non-reusable, meaning if we want another sample, we need a fresh CRS. It is roughly as long as the sample we want to produce. And the CRS cannot be uniformly random unless the distribution D is obliviously sampleable. And what does obliviously sampleable mean? It means that if we leak the random coins used for the sampling procedure, then we leak no additional information about the output. Just to give an example, RSA modulus are not obliviously sampleable, because if we give the random coins, we know the factorization. Okay. And yeah, if we have an obliviously sampleable distribution, we can sample securely from it just using a random oracle. We don't need interaction. Okay, so to summarize this theorem, we are saying without random oracles, actively secure distributed samplers are useless because they need a trusted setup, and the trusted setup is as bad as the one that we want to remove. Okay, finally, I can talk about the contribution of this paper, which is we came up with weaker definition of actively secure distributed samplers that go around the impossibility. So they don't need a random oracle. The first one is called hardness preserving distributed sampler. The second one is called indistinguishability preserving distributed sampler. The first one is basically a distributed sampler that preserves the hardness of search games, whereas the other one is a distributed sampler that preserves the functionality of the compiled protocol, so the protocol from which we want to remove the CRS. And yeah, this can be applied if particular conditions hold. Anyway, today I will focus on hardness preserving distributed samplers. I will explain the definition, and I will sketch how we built them. For indistinguishability preserving distributed samplers, I will only say a few words about which conditions we actually need to apply them. Okay, so let's start by taking a hard search game. So we have a challenger G and an adversary A, and we provide both of them with some challenge R coming from the distribution D. The two parties will interact. At the end, the challenger outputs a bit, represented whether the adversary wins or not. And since this game is hard, the probability of winning will be negligible. Now, hardness preserving distributed samplers are defined in a real world, ideal world paradigm. In the real world, we essentially have what I just described. The only difference is that the challenge R will now be a distributed sampler output, and we allow the adversary to actively corrupt a dishonest majority of the parties. Now, let's consider the ideal world. And here we substituted the honest parties with a simulator. This simulator will get as input an ideal sample from the distribution D, and it will use it to generate the simulated messages for the honest parties. At that point, the adversary will choose the messages of the corrupted parties, and the output of the protocol is fixed. It's R prime. And it may seem strange, but there is actually a non-negligible probability that R and R prime are different. And I will explain later why this is not a problem and how we will manage to prove security of our construction. Okay. Anyway, now our challenger needs a challenge for the search game, and we will use R, the ideal sum. And yeah, there will be interaction between with the adversary, and in the end, we output a bit. Anyway, in this ideal world, the challenge comes from D. This is a hard search game, so the probability that the adversary wins will be negligible. Now, in hardness-preserving distributed samplers, we don't ask for these two worlds to be indistinguishable, because actually they will be distinguishable, most likely, because there is a non-negligible probability in the ideal world that the challenge of the game is different from the output of the sampler. So what we ask instead is that if in the ideal world the adversary wins only with negligible probability, then the same happens in the real world. And now I would like to explain why this is an interesting definition. Now, suppose we have a protocol pi that relies on a CRS from the distribution D. And suppose also that we have some attacker that is efficient and for which we can efficiently tell whether it succeeded in its attack or not. And yeah, suppose also that there is some security requirement, a security guarantee with this protocol pi, namely the probability that this attacker succeeds is negligible. And here we are talking about probability. It's not like trying to guess a game. This is a bit. This is just an adversary that wins if it does something that it's not supposed to do. Okay. If we rely on a hardness-preserving distributed sampler, we have the guarantee that the compiled game, the one in which the CRS is generated by the distributed sampler, in the compiled game, the adversary will still succeed with negligible probability. So if the attacker is, I get into your bank account and I steal all your money, like even if we generate the CRS with the distributed sampler, I won't steal any money. Okay. Now I would like to explain how we build the hardness-preserving distributed samplers. And yeah, in order to do that, we introduced another notion of distributed samplers called lossy distributed samplers. And yeah, I need to introduce some notation. Let U be some fixed message for the distributed sampler of some party. We define the set omega of U as the set of all possible outputs we can get if that party sends this message. Essentially, we regenerate all the other messages and we consider all possible outputs that we get in this way. Okay, so the lossy distributed sampler has two modes of operation. The first one is called the standard mode. The other one is called the lossy mode. And the lossy mode is parameterized by some polynomial Q. So when the message U is generated in standard mode, the set omega of U will be big. It will have super polynomial size. When instead U is generated in lossy mode, the set omega of U will be small. It will be polynomial, and in particular, smaller than Q, the parameter of the lossy mode. And yeah, these two worlds will be distinguishable because we can regenerate all the other messages and see all the outputs. In standard mode, we have an increasing number of different outputs. In the lossy mode, this doesn't happen. At the end, we will get stuck in this small set of polynomial size. So we will have a lot of collisions if you want. Okay, so we don't ask for indistinguishability. What we ask instead is that it is possible to pick Q sufficiently large so that we can make the distinguishing advantage between these two worlds an arbitrarily small inverse polynomial function. So if you're familiar with the definition of extremely lossy functions, then it's basically the same. There is another property that we require from these lossy distributed samplers that is called programmability. And basically it says that in lossy mode, we can hide an ideal sample in this set omega of U. So these two worlds will be indistinguishable. In one case, we have the standard lossy mode. In the other case, we have an ideal sample hidden in it. But the size of these two sets is still smaller than Q. Okay. Okay, Now, yeah, in the paper, we show how to build a lossy distributed sampler under some set of strong assumptions, in particular sub-exponential I/O, sub-exponential multi-KFHC, extremely lossy functions that also require the exponential hardness of DDH for elliptic curves, sub-exponential collision-resistant hash functions, and also a new type of NISIX we introduced in the paper that we called almost everywhere extractable NISIX. And basically, these are extractable NISIX that are kind of compatible with I/O. So you can imagine that we have two programs that get as input some statement and a NISIC proving the well-formedness. And the first program will simply verify the NISIC. The second program instead tries to extract the witness. And we would like to argue that the obfuscation of these two are indistinguishable. And the issue is that there are different inputs usually. But if we use a almost everywhere extractable NISIC, we can argue that these two are indistinguishable by under sub-exponential I/O. Anyway, that's all I can say because of time restriction. So under this set of assumptions, we build programmable lossy distributed samplers that actually have a CRS. But this CRS is short. In particular, it's independent of the distribution we want to sample from. It's reusable. And there is an instantiation of the construction so that it's also uniformly random. So if we have to rely on a CRS, it's the best CRS possible. Okay, now I would like to prove to you that any programmable lossy distributed sampler is actually hardness preserving. And we will do it by contradiction. So we take a hard search game, and we assume there exists an adversary that wins the real-world execution of the hardness preserving distributed sampler with non-negligible probability epsilon. So anyway, here the messages of the parties are the lossy distributed sampler messages in standard mode. So if we pick our favorite honest party, P2, and we consider omega of U2, this will be big. And R, the output of the distributed sampler, will belong to it. Now we proceed using a hybrid argument, trying to reach a contradiction. And so we move to hybrid 1. And here we switch the message of party P2 from standard mode to lossy mode. And yeah, all of a sudden, the set omega of U2 becomes small, polynomial in size, and R still belongs to it. There is a small issue, like this hybrid is clearly distinguishable from the previous one because standard mode and lossy mode are distinguishable. But yeah, if we pick Q sufficiently large, we can still argue that the adversary A wins the game with non-negligible probability, a bit smaller than before, but greater than epsilon divided by 2. Okay, hybrid 2. Now we use programmability. So we get an ideal sample from the distribution D, and we hide it in the set omega of U2. And yeah, after sending the messages of the honest parties, the adversary will pick one of the elements in the omega of U2 as output of the sampler, and we will use it as a challenge. Yeah. And yeah, hybrid 2 and hybrid 1 will be indistinguishable under the programmability of the sampler. So the adversary will still win with a non-negligible probability. But now something interesting happens because the set omega of U2 is small, it's polynomial in size. So the adversary will end up choosing R prime to be equal to R with inverse polynomial probability without even realizing it, actually. And so if we consider the probability that the adversary wins and R is equal to R prime, this will be non-negligible. But now we reach the contradiction because, I mean, if R is equal to R prime, the challenge of this game is an ideal sample. And we assume that the game was hard to start with. So we have an adversary that wins the search game with non-negligible probability. And so, yeah, this is the end of the proof. That's all about hardness preserving distributed samplers. I would like to say which conditions are needed in order to apply indistinguishability preserving distributed samplers. And yeah, suppose that we have a protocol as in the slide. So it gets a CRS from some distribution D. And suppose that this protocol implements some functionality F, as you see on the right side. So basically here, the simulator is split into two parts. First, it simulates the CRS using this distribution D prime, and it will give R prime the fake CRS to the adversary, and it will pass on R prime and some trapdoor T to the second part of the simulation. The second part of the simulation will interact with the functionality and the adversary, and it will make sure that the ideal world is indistinguishable from the real world. Okay, in this context, we can use indistinguishability preserving distributed sampler to remove the CRS from this protocol pi and be ensured that the result still implements the functionality F. But the important point here is that not all protocols satisfy the condition that you see on the right, because we ask that there is no interaction between the first part of the simulation and the functionality. And this is important. In particular, in general, the simulator will start by talking to the functionality, get some information, and it uses it to simulate the CRS. Here, we don't want that. Okay. In the paper, we show that our lossy distributed sampler is actually indistinguishability preserving, but not all lossy distributed sampler are. Okay. Finally, I want to conclude by talking about the relationship between distributed samplers and CRSs, because all our construction need a CRS that is, however, reusable, short, and unstructured. But can we get rid of the CRS completely? And yeah, it depends. So for indistinguishability preserving, no. And that's because we can compile any active 2-round OT like the one in PVW, and we would get a 3-round active OT in the plane model, which is with black box simulation, which is impossible. But for hardness preserving distributed sampler, the question is open. Maybe we can construct them without CRSs. Anyway, in the paper, we show that if we weaken the security requirements, it is actually possible to get rid of CRSs, even for indistinguishability preserving distributed samplers. And we do this if by restricting the security model only to uniform adversaries and by allowing the simulator to be non-uniform. And yeah, we could achieve this because in this setting, it is possible to build NISICs that don't need the CRS. In particular, we build NISICs that are simulation extractable and without CRS. And yeah, that's all for the talk.
There's some time for questions. If you have a question, please come at the microphone. Okay, so while we're waiting to see if there are any questions, what's your intuition of removing the use of IO? Like, what is the hardness?
Sorry, can you repeat?
What's your intuition in removing the use of IO from your construction?
I mean, IO is needed, or at least, wait a second. For indistinguishability preserving distributed sampler, I'm quite confident that we need that. For hardness preserving is a bit unclear, to be fair. Yeah, but I wouldn't know where to start from, to be clear. Like it's a quite complicated construction and primitive in general.
Are there more questions? Okay, then let's thank Damiano again. Let's thank all the speakers of this session. You can go to the barbecue.